Hello everyone, welcome to the next lecture where we are going to start the more difficult part of the course, which involving starting from general probability spaces and other materials which we have seen in discrete time. But now when we are moved to the general one, which is essentially means the continuous time cases we are going to encounter. But what we are going to do is that we will just recall some of the things which you know, and we might state most of the results as only results and without proof, but the results are similar to what you might have seen in discrete time, but the proofs are a bit technical, and since our objective is not essentially to master the stochastic calculus part, we will take the results as given and we will go ahead and we will try to apply those results into the financial field, which is what our objective is, and hence many of the results that we would see in the next maybe about 6 lectures, what you would see is the results that is required for application into the financial market models that we are going to deal with it. Okay. So, this part is what we would consider as stochastic calculus. Of course, one could have a full course on that itself, but we need it. So, we will just briefly take that input and then we will go ahead with it. Okay. So, let us start with the basic idea of general probability spaces. Specifically what this means is that we are considering, since we have already considered discrete probability spaces. So, what we are actually considering is essentially the infinite probability spaces, where what we try to model is a situation wherein the random experiment results in an infinite number of outcomes rather than being a finite or countable number of outcomes. So, some would say that it is uncountably infinite or everything, but for us that would be sufficient. So, basically what we have in mind is this infinite probability spaces is what we have. For example, if you pick a random experiment which is of choosing a number from the closed interval 0 1 is one such experiment that you can think of, and the other experiment is basically toss, since we are so accustomed to coin toss experiments. So, we can say a toss a coin infinitely many times. Okay. So, this is what is the two immediate examples that we can see. Of course, the first one is what we are going to consider for a little bit more elaboration. The second one is along similar line. So, what we have now is suppose if we write down the sample space, for example, for these two cases. So, in this particular case, this omega would be this, which you see has an infinite number of elements in this omega. And in this case, the omega is the set of all omegas such that this omega can be expressed as omega 1, omega 2, omega 3, just like in the earlier case, where each of these omega i's are either head or tail, right. So, this is what you would represent your the infinite coin toss sequences. It could be as an infinite sequence of heads and tail, H and T is what then you would. Okay. So, this is the sample space, and we also have on this sample space a sigma field or a sigma algebra. So, the definition which we have already seen stands true even in this particular case, which is basically is a non-empty collection of subsets of the sample space omega, which is closed under countable union and complementation, right. So, that is what is a sigma field or sigma algebra, which we have already seen, and on which we also define a probability measure, the definition stands again exactly the same as the previous one. Just kindly recall that it is a mapping from omega to 0 1 or omega to r such that each of those elements in F have probability assigned between a value 0 and 1, and probability of omega is 1, and the if you take set disjoint mutually disjoint sets AIs from omega, then their union of their probability of their union is sum of their probability, which is what we call countable additivity property is what, right. So, this is a probability measure which satisfies this. Okay. But now, if you recall in discrete time how we have defined or how we have specified the probability measure on the sigma field that we consider. Okay. What we did is basically we took the elementary events or sample points from the sample, and then we assigned non-negative numbers to that and such that they sum to 1, and for any other event A we defined the probability of that event A to be the sum of the probabilities of the elements in that set, finish, right. But the same thing will not work here, because you would see that, for example, if you take this omega as 0 1, right. So, the sigma field and a typical nature of this continuous probability space or infinity probability spaces are that each of these sample points carry a probability of 0, right. So, this is all you can recall from your probability theory idea, and in such a situation there is no way that you will assign probability such that this, and then and also when if you want to extend that, there is nothing like an uncountable sum, something like that you can talk about it. So, we must have a different way of assigning probability measure in such situations, and so what is done is, rather than assigning probabilities to individual elements, the probabilities are assigned to certain sets, and you assume or you ensure, right, that by defining that there are many subsets for which also the probability get assigned automatically by the properties of the probability measure. Say for example, now we will take this simple example of this omega, right. So, we will take omega to be 0 1, this is our sample space here. Now, what we can do is that we can define probability of closed intervals in 0 1 as given by its length for A and B. So, probability of A B, the closed interval, is simply given by B minus A, where this, and those of you who are familiar, you will also know that this is also called as the Lebesgue measure, right. Okay. So, now by defining this, there are many subsets of omega whose probability is determined by this P and the properties of this probability measure P, right. Say for example, if you consider the open intervals, since open intervals can be written as unions of closed intervals, right. So, you can apply that, and then the limiting continuity property of P would ensure that the open intervals also has the same probability as right. So, example case is, say probability of open interval A B would also mean will be assigned a probability of B minus A. So, what we are appealing? We are appealing to the properties of P, right, and then we consider all possible open closed intervals in 0 1, which is what is of the form A to B for arbitrary A and B, and then since you can write this, so you will get this. Similarly, you would obtain probability of say for example, say some interval. Suppose if you take say half to 3 by 4 union, right, say 0 to 1 by 3, right. So, you would see that This is again you can write it as probability of this first interval plus the second interval property of P, then each one of them can be applied here and then you can obtain the probabilities here, right. So, this way there are many sets and for which the probabilities of all the probabilities gets assigned automatically, okay. But what is this collection, right? What is this collection of sets for which the probabilities are getting assigned by this process, okay. That collection, so what is this collection of events, right? These are all events connected with this. So, what is this collection of events for which the probabilities of gets assigned in this manner, which essentially means if I take closed interval a b, all possible closed intervals, and I add whatever it is to make this collection as a sigma field or sigma algebra, that is what this collection, and this collection is what is called as the Borel sigma field of subsets of 0 1, and it is also denoted as Borel 0 1, because we started with the interval 0 1, took the class of all open intervals as generators, what we call, and formed the sigma algebra, which is what is called the Borel sigma field, Borel sigma algebra over 0 1, which is sometimes written in this form. Okay. Now, extending this idea, suppose instead of 0 1, so in on R, so what you will have, this is okay, you can call it this way or this way. So, this is what is the Borel sigma field on R essentially, which is actually Borel sigma field of this, and a set B which is belonging to this is called a Borel set. Okay. Now, in the whole of thing, so this is the sigma field with which we will be concerned with, because this is what is the sigma field with which we can assign probability measures on subsets of this Borel. There are in measure theory, those people who are aware about measure theoretic idea, there are non-Borel sets, but that is not of interest to us. So, essentially we will be confined ourselves to, when we say a subset of R in the whole course, we mean a subset which is a Borel set, right. So, that is what anything that is what it will be concerned with this case. Okay. Now, so this is what is, so this is the collection on which this P is getting assigned. Now, I mean it is not possible to enumerate all the sets and all the probability measures that we have, but you know there are singleton is a Borel set, a finite set is a Borel set, countable set is a Borel set, you know an uncountable set, interval is a Borel set, an open set is a Borel set, closed set is a Borel set. I mean almost all what you can think about with respect to real experiments, all such things would be there in the inside this Borel sigma field. So, we will be happy to deal with this itself, we will not look beyond this. Okay. So, going forward anything, any subset of R which we talk about is a Borel subset, and the sigma field that we consider over R is the Borel sigma field, right. That is what you know we will have. Now, there is I mean as I said, you know many things like we will just recall the results and we will be using it frequently, the terminology. So, the next terminology that we will go on to see. So, here in continuous probability spaces or infinite probability spaces, you have this problem that you know somehow if you take an uncountable set, say 0 1 itself or 0 2 half, you see that each of these points have probability 0, but if you put together 0 to half, it has probability half. I mean according to, for example, this is typical example that we have considered just now. So, this is basically you know a side kind of little bit uncomfortable some people might feel, but that is the nature of the subject. Okay. So, what we will do is that we will define such things by you know doing some kind of terminology, right. What we say is that one definition is we have a probability space omega f p as usual, and if there is a set A in F is such that probability of A is 1, then we say that the event A occurs almost surely. So, this is the word that we will be using. Equivalently, in the engineering literature, you will also find the usage with probability 1 is what is also used equivalently. So, this is what is the word almost surely. This is one form of. So, what does that mean? So, which means that probability of A is 1. If there is an event A, simply a subset of omega which is there in F, for which this P of A is 1, then the event A is said to occur almost surely, or if this A represents some property, then we say that the property holds with probability 1 or the property is true almost surely, right. Which means what? There are situations in which this is not true, right, but those together carry a probability of 0, right. So, if you go back to the previous 0 1 interval, you know that if you take a set of all rational numbers, since it is countable. So, if you take their probabilities, it may be 0, right, but that is what it means. So, which means that this is what then you will have in this case. Okay. So, this is the definition that you will have with respect to probability. The next thing that we will go is essentially the idea of random variable. We already have seen idea of this random variable. What is that random variable? We have seen x is a mapping from omega to r such that x belonging to B is in F for all B in B of R. So, this is the general definition where what is this B? B is the Borel set. So, if this is true, a real valued function on omega such that its inverse image of Borel sets R in F is what then is a random variable that we have. Now, associated with this you have what we call distribution of x, right. Distribution of x we define to be p x of B, which is essentially probability of x belonging to B. Again B is a Borel set. So, this is what we call it as the probability measure. This is this probability distribution of x. Remember, this is different from the distribution function that you might have been aware, but this is probability distribution. So, this is also a probability measure, right. P x is also a probability measure, which means that it satisfies the axioms of probability measure, right. So, you can assume these two concepts are different, random variable and distribution. In finance, that you need to keep this idea in mind. Random variables and distributions are two different concepts. The random variable can have different distributions, and there could be two random variables which have the same distribution. So, these things you have to keep in mind. One other way in which the distribution is being represented and which you have been knowing is to record the distribution of x is, see, the other way or the alternate way is through what you call cumulative distribution function, right. This also records the probability distribution of x, and what is that? You have already, those of you who are familiar, recall that this is nothing but this function, and remember this is nothing but, if I write x less than or equal to x, I can also write this as probability of x of omega or x, sorry. So, this x belonging to this quantity, right, is what is x. So, if you see minus infinity to x is a Borel set. So, this is essentially same as this p x, but we are taking a specific form of B rather than taking for all Borel sets B as given here. We take for all x in R, which means you extend x, you take only the form minus infinity to x and keep varying x. So, you have one class of sets. This also will generate the same Borel sigma field that you have it here. Okay. Now, in two special cases where this distribution can be recorded in more detail, or one in discrete, okay, two special cases in which the distribution can be recorded in more detail is, one is this discrete, which is essentially meaning this is sum over I such that your x I is in B of this p i's for all Borel sets B. Okay. And what are these p i's? This p i's is what the collection, p I is what the PMF of the random variable x. The other case is essentially p x of say A to B. If I take, then this is this quantity for minus infinity less than A less than or equal to B less than infinity, and in this case this is discrete, and this is we call continuous random variable, right, and this f is what is called the probability density function, and this is what call this pi as the probability mass function, which you have seen already in discrete time. So, these are the two cases in which you can record the details, these two special cases in which you can record the distribution function in a much simpler form in more detail. Of course, there are random variables which has a part discrete and part continuous, which are called mixed random variables, and there are random variables which have neither a probability mass function nor a discrete density function. Okay. Even in finance field also, like they do have application, but that is much more advanced level. So, elementary level what will be concerned, just like in the discrete case we assume that there is a PMF. In the case that we are going to consider, we will assume that the random variables is continuous and it has a PDF, and hence the probability measure would be equivalently described by the PDF that we may have. Okay. Now, once we have this random variables, the next thing that we consider is the expectations, right. We have seen in discrete also, after this expectation. Now, here the expectation of x, okay. So, for any random variable x, for a random variable x, the expectation of x is defined by this quantity. Now, this I write, but we will see what this is in a moment. Okay. I write this as integral over omega, which is x of omega dp of omega. Recall, this is something similar to what we have seen in discrete. In discrete, what we have written, expectation of x is summation over omega belonging to omega x of omega p of omega, right. So, this is in a way much similar, but there it is a countable number of omega at most. So, there was a sum, but here uncountable. So, this is okay, but we need to make sense of what is this quantity. I will just come back in a moment. This this definition would make sense provided this exists. Okay. So, note, I will just say this makes sense if this is defined in a way. Okay. Now, what is that? We will see in a moment. Okay. So, there is a particular case in which this quantity is not defined because this will not make sense. Okay. Now, what is this quantity? Okay. So, this omega integral over omega x of omega d of p omega is what is called, or we are writing this expectation of x in terms of this as the in terms of Lebesgue integral, right. So, what we have? So, this is a form of Lebesgue integral. Now, those of you who are familiar with what is this Lebesgue integral, okay, can skip this part and quickly move to maybe another 5 minutes later. But otherwise, you can see what we mean by this. Okay. So, this is x dp in short, x of omega d of dp of omega, this is what it is. Now, what is this quantity, or how do we define this quantity? That is what we are going to see. And so, what is this quantity is what then we are going to see. Assume first, okay, assume that this whatever the x that we are considering is basically is a non-negative quantity for all omega in omega, okay, and let this I call it as pi, which is a set of numbers y1, y2 and so on, be the set of partition points, okay, where what we have, since this is non-negative, so we pick y naught which is equal to 0, and then the next value is y1, next value is y2 and so on. Okay. Now, for each subinterval which is of the form yk to yk plus 1, we set the set ak to be the collection of all omegas which gives value of this random variable lies between and including the left, but not excluding not including the right side, right. So, this is the set that we call. Okay. So, this is what we have it here. Okay. So, now the Lebesgue integral is what we are talking about. People who are familiar with Riemann integral, which is the ordinary integral, there what we do, how do we compute, or how that is defined? You partition the x axis, which is the domain, right, and then just like here the partition this is, and then you take the lower Riemann sum or upper Riemann sum or in general Riemann sum, and as the partition points are getting increased, in the limit that lower Riemann sum or upper Riemann sum would converge to a value, that is what you call the Riemann integral or simply integral, that is what you are using. Similar here, if you look at, this is what we have, and then we are looking at not on the x axis the partition, but on the y axis. The reason is that x is a mapping from omega to R. This omega could be any abstract set, need not be a subset of R, where you can make some ordering properties there. So, you can make a nice partition, but since y axis is real number, so we make partition y axis and then we try to compute. That is what is the Lebesgue integral is, right. Now, we define the lower Riemann sum in this particular case with respect to partition, the lower Riemann sum, Lebesgue sum, the lower Lebesgue sum with respect to the partition of with respect to this function x as summation k is equal to 1 to infinity yk probability of a k. Okay. So, this is what you see as the lower Lebesgue sum, and this converges as the norm of this partition approaches 0, and we define the limit, right, the convergent, the quantity which is this limit to be integral over x of omega d p of omega, or simply, for simplicity we may always write in this form. Okay. So, this is what it is. Okay. I mean, we are assuming simple cases, so there is not much issue. So, we say that this lower Riemann, you could again do similar thing like upper or any Riemann sum, but here if you see, you have to pick the yk multiplied by p probability of ak, and this quantity converges. Okay, this converges as this norm of this partition. What is this norm of this partition mean? The length of the largest subinterval of this partition y pi, which is in terms of this y's that you have here. Okay. Now, note that here this could even be infinity, right. So, this limit or this Lebesgue integral, we did not restrict x. So, this sum could even be infinity, we do allow. Okay. So, this is could be infinity also, this quantity, right, because this non-negative quantity and we are summing over some non-negative multiplied by some proportions. Now, this is non-negative. Now, for general x which takes both positive and negative values, what we do, first we define two quantities, which is x plus of omega as maximum of x of omega 0 and x minus of omega as maximum of minus x of omega comma 0, and we call this as the positive part of x and the negative part of x, and my x then you can see is given by x plus minus x minus, and mod x is simply x plus plus x minus. These are the, you can easily observe that by defining x plus x minus, the positive and negative parts, the any general x can be written in this form and mod x could be written in this form, right. Now, when you can write in this form, you can see both x plus and x minus is a non-negative quantity, and the previous discussion of x being a non-negative and the definition of integral over x dp, right. So, you can define x plus dp over omega and define this and integral over x minus dp as above, just like the non-negative case that we have considered. Now, since we said that this is, each one of them can take the infinity, the value infinity, right, and if provided both of them are not infinity, you can define this omega x dp as omega x plus dp minus this x minus dp, provided both means here integral over omega of x plus and integral over omega of x minus dp, both are not infinity, right. If the first one is finite, the second one is infinity, then you can define this to be minus infinity. If the first one is infinity, the second one is finite, then you can define this to be infinity. But if both of them are infinity, then this is not defined. So, this is what we mean when we define expectation of x, provided this is defined, we mean that this particular integral is defined for any x. Now, we have a special name which we will need when which is the case of both are infinity, sorry, both are finite, sorry. What is this? If both are finite, okay, then we say that x is integrable, okay, and in this case you can observe that integral over mod x of omega dp of omega would be finite, because in this case mod x is simply x plus plus x minus. So, both of them are finite. So, the sum is finite and hence this is finite, right. So, this is what we mean in this case. So, this is the first part. Now, one more thing which you can you have to note it down is essentially, instead of taking this Lebesgue integral over the whole set omega, we often might have to take over some subsets of omega, some subsets Borel set, some in A, but you can see that this could be written in terms of the indicator function that we are aware already. So, this is true for all A in F, that when we mean the Lebesgue integral over some subset of A, we mean you can also write in this form using the indicator function for computation. And another quantity that we will need is what we call the following. Okay, the definition essentially. So, you have a function from R to R, and if for every Borel set, this set of all x such that my f of x belonging to B, right, is also a Borel set, then f is what we call Borel measurable. Okay. So, Borel measurable. So, this is what is the definition that we call. Okay. Now, what are the Borel measurable functions? Normally what you encounter, the simple function that we always encounter, they are all Borel measurable functions. Say a continuous function is a Borel measurable Borel function, a step function, increasing function, or these all of them are Borel measurable functions that you normally encounter. So, again, just like we said that any subset of R throughout we mean a Borel subset, any function of a real valued function that we are considering will be a Borel measurable function only from now onwards throughout the course. So, without any time repeating, we always mean a function, a real valued function means a Borel measurable function, which is in this sense it is true, which means what? The inverse images of Borel sets are Borel sets again, right. Now, why do we need this is basically when we have defined Lebesgue integrals, but how this compares with the Riemann integral that we already know of. Okay. The comparison which is what will help us in computations of this Lebesgue integral or expectations since we define to be this, or whatever you already know, we should also see that whether that is same as this one. So, that is if the Riemann integral say over some a to b of some f of x dx is defined, then what we can say f is Borel measurable and the Riemann and Lebesgue integrals agree, means they coincide. But there are situations where these will not agree, but in that case if the Riemann integral exists, if we put that condition, if the Riemann integral exists and is defined, then this is that f is Borel measurable and the Lebesgue and Riemann integral are one and the same. So, this gives us a way to write down the expectation which we define in terms of Lebesgue integral to also write in terms of the easier and much more convenient form in terms of Riemann integral, so that our computations can go well. So, this is something similar to what you might have seen in the discrete case. So, let us quickly see that. So, what we have, the result is the following, which is after a couple of steps you will obtain this result, but since we are not worried about that. So, let us take the result, that is what we have. So, x be a random variable on some probability space omega f p and let G be a Borel measurable function on R. Okay. Also, suppose this random variable x has a density which is essentially means that is PDF, okay, f, right, x has a density f. Then, so what we are claiming? Then expectation of this quantity is given by, sorry, this is small x f of x dx, and if this quantity is finite, then expectation of g of x is simply given by this. Okay. So, now you see, right, you are seeing something which you are already aware about it, expectation of g of x, right. But much more general is what we have defined, which could even include the case infinity in some cases. But whenever this is defined, which means this is defined, right, and then if this quantity is finite, then only we define expectation of g x to be this, which is what in the normal probability course you would have seen as expectation of g of x is defined, or simply expectation of x is defined in this case, okay, which is also much similar to this is if when x has a density f. Suppose in case of discrete, what happens? You just replace this sum by this integral by the sum. So, you get your discrete case what we have defined as the expectation. This is the case. Okay. So, once we know about this Lebesgue, I mean expectation of x, again we will just recall certain properties. A, if x less than or equal to y almost surely. Now, you see in continuous time we start using this, we do not require x less than or equal to y for all omega. We only need almost surely sense x less than or equal to y. Then this, if this is the case, then expectation of x is less than or equal to expectation of y, because expectation of alpha times x plus y is alpha times expectation of x plus expectation of y, and if you take a phi is which is convex function, then phi of expectation of x is less than or equal to expectation of phi of x, which is what we call Jensen's inequality. We have seen in discrete also, it is exactly so true here, right. So, like this you can list a property, but this properties if you apply this definition of Lebesgue integral sense in like in discrete case, this is also follow very quickly, right. Many of the statements that we might write, we may take it in the almost surely sense, still the result will be true. That is the beauty of this continuous time models that you might consider. Okay. Now, we also have to talk about, when we talk about random variables or sequence of random variables, we may also have to talk about convergence of, but in this case what we are interested, of course, in probability theory there are at least 4 type of convergence that you are aware. We will just recall what is convergence almost surely or convergence with probability 1, right. So, what we have a sequence of random variables, So, we say, and there is another random variable x, all defined on the same probability space, and we say that x n converges to x almost surely if, right, the probability of omega right, such that the x n of omega converges to x of omega is 1. What does that mean? Once you fix an omega, right, then this sequence of random variables x1, x2, xn are going to give a sequence of real numbers, right. Now, what is that real numbers converge is what is given here, x of omega, right. So, you collect all those omegas for which this convergence takes place, right, and if this collection of omega carries a probability 1, then xn converges to x, which is in a way equivalent to your pointwise convergence that you are talking about in the normal sense, right. But there are omegas for which this xn does not converge to this particular x, but together they carry probability 0, right. So, the same thing you can also write xn of omega does not converges to this particular, but this carries probability 0, because this is the complement is okay. Now, the question will come, which is what relevant to us in many situations is suppose if I have a sequence of random variables, okay, the question is if this is sequence of random variables is there, whether this convergence carries over to the expectations, right. So, which means whether is it true always that expectation of x is given by limit of as n tends to infinity of expectation of x n. Essentially, you are saying expectation and limit operation you are trying to interchange, right. Two results which we would require is one is called monotone convergence theorem, MCT, which means monotone convergence theorem. When this is true, suppose if these are all non-negative, it is 0, x 2 and they are increasing almost surely, then suppose if I call this as star, then star holds. Okay. The other case which is given by what we call dominated convergence theorem, if there exists another random variable y, if there exists another random variable y such that your expectation of y is finite and these xn's are bounded by y almost surely, then star holds. Okay. So, we give two conditions, two different conditions under which the limit and expectation operators can be interchanged, which essentially means that when xn converges to x always, okay, is it true always with condition is xn converges to x almost surely, right. Then whether this is true, then if this is increasing non-negative and increasing, then of course star holds, and if there is y which bounds. So, this is dominated convergence theorem and that is monotone convergence theorem. Under these two scenarios, you can show that these are the two famous results in measure theory, which we might use whenever need a little later, whenever we talk about a sequence of random quantities converging, right, and that is what we will see. Okay. Now, what you have the next idea is basically more relevant to our field, which is the financial whatever we are going to deal with is this change of measure idea. Recall that in discrete also we had considered two probability measures p and p tilde, right. So, but how did these two quantities p and beta, how are they related is via a quantity called z, which we call a Renan equilibrium derivative, right. So, you recall this quantity is we wrote, right. So, this is what it is in discrete case via this z. Okay. So, now in continuous case, of course, since p and p tilde here we could define and we could easily get it that both of them are strictly greater than 0. So, you could define it in this manner, but in continuous case of course, for individual omega this is 0, and even if you write this equation as p tilde of omega as equal to z of omega multiplied by p of omega, still both sides are 0, does not tell you anything. But this gives the idea of how to get a p tilde out of p. I mean, the idea is you have to somehow use this z, right. So, in which case what we have is this specific result, which is what is we will use. So, this is what, let us quickly go through. So, you have a probability space be a probability space, and you have an z which is greater than 0 almost surely, and you also have expectation of z is 1, which means z is equal to under probability p, this is 1. Now, for A in F, define my p tilde of A, which is equal to right. So, you define p tilde, you see if you rewrite the earlier discrete case, you could write p tilde of omega as z of omega p of omega. So, this is in spirit captures that same idea, but now since you cannot talk with respect to each omega because both sides are equal to 0. So, you talk in terms of events, in terms of sets in F, that is what is the idea essentially, right. Then what we have, this quantity is a probability measure, which is the first statement. Furthermore, this relationship, which is you have also seen in discrete case, x is z for x non-negative. In a moment you will know why we say x non-negative on this condition. So, E of y is essentially y by z for y non-negative. Okay. Now, note for general x, the above two equalities connecting expectation under E and under P and P tilde, the above two quantities is the above two is applied to x plus and x minus, and provided they will make sense provided infinity minus infinity case is not occurring, right, is not occurring. So, if that is the case, of course, these things are not defined, so nothing you can talk about it. Whenever we say that whenever this is defined, which means that this infinity minus infinity case does not occur, in all other cases you can talk in a similar way. But for the result mainly, like you can consider x non-negative, that is sufficient, because in this particular case you will going to apply individually. So, this is what is the result, right. What this says is it captured the spirit of what we have done in the discrete case. So, you pick a z which is greater than 0 almost surely, we need only almost surely, and expectation of z is 1. These are the two properties that you require for z, and this is what is this required. And if you have that z, and in discrete also you have seen these two properties are satisfied, and if you have that z, of course, you will get this p tilde, and in fact, to get this p tilde even you do not need this z non-negative is sufficient, but for some other purpose we need z strictly greater than 0. So, we will keep that, otherwise this last equation that we wrote here, again you have to assume z to be strictly positive. So, we generally assume z to be positive case that you have here. Okay. Now, this is the way your things are related in, they are defining in this case. Now, this leads to my next definition, which is after giving this definition, then we will see why and hence and what. So, you have omega be a non-empty set and F a sigma field of subsets of omega or a sigma field over omega, then two probability measures, say P and P tilde on P and P tilde on this omega f, which we call as a measurable space. Again, without this P attached to this, we are considering this a pair, are said to be equivalent. Remember, this is the technical term here what we are defining. If they agree which sets in F have probability 0. So, we say P and P tilde, two probability measures defined on the same omega f, this pair, are said to be equivalent if they agree which sets in F have probability 0. Alternatively, this would also imply that they also agree on which sets have probability 1, which means which are the sets which are almost surely going to occur, which are the sets which are almost surely not going to occur, right. So, that is what the equivalent probability measures property that we have here. Now, so once we define this, right, now our what we state is that claim, which you can verify, is P and P tilde as defined earlier or above are equivalent. Okay. Just the previous result that you recall, we have defined P tilde using Z, and that these two measures as are under the condition that is specified in the result, they are all equivalent. How do we see? This is a quick proof, since this is you required to know. So, you will just quickly do this. Suppose you pick a A in F such that your probability of A is 0. Okay. Z as it is, Z is strictly greater than 0 with expectation of Z is 1, and you are picking an A such that probability of A is 0. Now, this should imply that P tilde of A is also 0, right. Now, how do we see this? So, since this is 0, you can see that the random variable indicator function of A and Z, right, Z is strictly greater than 0, indicator function of A is 1 for omega in this one, and otherwise this is 0, right. On a set of probability A, this is 0, right, and Z is greater than 0 is what that you have. You can see that this is equal to 0. In what sense? This sense. Almost surely this is equal to 0. This quantity is almost surely equal to 0. So, this implies my definition of P tilde A, which we have here, is essentially omega I A is at dP, right. Probability of A is integral over A of Z dP, which is exactly equal to I A Z times dP, but I A Z is equal to 0 with probability 1. So, this is equal to 0. So, P of A equal to 0 implies P tilde of A equal to 0. Okay. On the other hand, suppose you take a B in F such that your P tilde of B equal to 0. What does that mean? This means that this quantity 1 by Z indicator function of B, this is equal to 0 almost surely. I am writing the same statement slightly differently. Okay. So, what does this imply? This imply, so almost surely under P, so under P tilde, sorry. So, this is I have to almost surely, so we have to write P tilde almost surely. So, this means that E tilde of 1 by Z I B equal to 0, which is equal to expectation of I B, which is equal to probability of P. So, probability of B. If I take P tilde of for a B, but for which P tilde gives probability 0, that also implies that P also assigns a value 0. So, and hence this claim, which is these two are equivalent, is true. Okay. Now, as we said, equivalent means that this is also saying that they also agree on which sets in F have probability 1. Okay. Now, why do we require this here? Because we look for, just like in the discrete case, we look for the equivalent probability measures is what we look for. So that just recall what we did in discrete. We had a discrete time model for the financial market. Their actual probability measure was P. We did the pricing under P tilde and we did construct the hedge under P tilde, and the hedge worked well in the real world. That is what we have seen. This is the cycle that you close. You start with P and then you come on close to the P. Now, how did this work? Because the P tilde that we considered there was equivalent probability measure. So, same thing here. So, we look for it condition also, we need to look for an equivalent probability measure. So, that we have a probability measure which is P, which is a real world probability measure, and we consider an equivalent probability measure which is risk neutral measure. Now, that we can use the terminology since you are aware about it, risk neutral measure. And if this risk neutral measure is equivalent to risk, this actual probability measure or real world probability measure, then this risk neutral measure is you can use to price the derivative, construct the hedge. Now, since the hedge is going to work in risk neutral world in a sense, or in almost surely sense, it will also work in real world almost surely sense if these two measures are equivalent. So, what we look for in this model is again to construct an equivalent probability measure in this case. Okay. So, what do we call this? I mean, the definition is basically such an Z that we you take all these things, omega f p be a probability measure and p tilde be another probability measure such that they are equivalent, and let be a Z be a random variable with those properties, right. So, that is Z greater than 0 almost surely and expectation of Z is 1. Then what is that Z is called? So, that Z is what is called as Radon Nikodym derivative, and we write this Z as dP tilde over dP is what then we write. This is, so this is the Z that we are. Now, to construct an equivalent probability measure, we need an Z. Now, suppose if I have two probability measures P and P tilde which are equivalent. Now, does there exist an Z? Only if I am sure that there exists an Z, I can construct that build that Z in some way or other, right. So, that result is what is guaranteed, and the only way you can get the equivalent probability measure is the way that we have defined in the previous result. So, you need an Z. Now, does there exist a Z such that that is there? The result is what is called as the Radon-Nikodym derivative theorem, which is what is the following. Now, let P and P tilde be equivalent probability measures on which are defined on omega f. Then there exists an almost surely positive random variable Z such that expectation of Z is 1 and P tilde of A is essentially given by this. So, this is what guarantees that there exists an Z. So, what are the properties that you look for? Z greater than 0 almost surely and expectation of Z is 1. So, if you can find out an Z such that, so this radon equilibrium is guarantees the existence. If there are equivalent probability measures, then there is an Z with the required properties. You just have to find what is that Z, and that is what is called Rn radon equilibrium derivative or simply Rn derivative, as we have seen in the discrete case. The terminology is familiar, but this is the more general case that we have here. Okay. So, these are the basic ideas from the probability theory that from discrete and continuous when we want to move ahead with these things. Okay. So, yeah, so we will continue with the remaining in the next lecture.